during the last talk, chemistry was already mentioned a lot of times. And chemistry is a very important other factor. And so related to microbiology, but also separately, it's very important. So therefore, I'm very glad that the next speaker will be able to tell us something about it. She's Dr. Catherine Peters. She's the George G. McGee Professor of Geosciences and Geological Engineering at Princeton University. And she's an expert in environmental chemistry and geochemistry, known for her leadership in sustainable energy technologies. So that's very relevant for subsurface hydrogen storage. She's a fellow of the Association of Environmental Engineering and Science Professors and served as president in 2002. And what is very interesting, what I saw in your LinkedIn profile, that you prefer to have a combination of both experimental and modeling techniques and a variety of technologies to know more about chemical processes, which is very interesting. And I also heard from you that you're currently doing a sabbatical at Hari's lab, so that's a nice link. Yeah.
Yes.
So looking forward to your presentation.
Thank you for reminding me about my LinkedIn page, which I haven't updated in years. But you found something relevant there. That's true. Thank you, everyone. I'd thank Hadi if he were in the room. It's really a pleasure to be a part of this workshop for the second year in a row. And it's a pleasure to be in this session with Nicole, because I think the things we're talking about are the same, and there's a microbiological side and there's a chemical side. And I come at this from the chemistry side, and I have a bit of different perspective on some things. First, I'll say that my name is the only name there because I'm the one standing here talking, but I want to acknowledge that I am going to present some research, and quite a bit of it was done with the help of students and postdocs, but including a colleague at Auburn University, that's Lauren Beckingham, who got involved in this research with me the past year. And I will tell you that the research we did that I'm going to present was inspired by coming to this event last year. And so we have some preliminary results to show you. Oh, I can use this. This button? No. Oh, now what did I do? Great. All right, I'll start. I love this graphic because it shows the subsurface environment and options we have for storing gases in general. We have the salt dome option and we have the porous media option. And this issue, and I think that Nicole at the end of her slide said salt cavern versus porous media. This is a great question, especially in the United States where we have fewer salt domes. And so the important thing for me is that the mineralogy and the geochemistry of those two formations is completely different. And we talk about them being different in geophysical ways and hydrologic properties, but we also have to talk about them in terms of the differences in terms of the geochemistry and the mineralogy and the microbiology. So that's what I'll get into. And I just will include a little bit of information there about salt cavern storage of hydrogen in the United States. This is not an audience that needs to learn about salt domes, but I wanted to include this because this is a nice ocean floor view of salt domes in the Gulf of Mexico, south of Louisiana. But I don't see my Louisiana colleague here today. Okay, this is what I want to show you. This is from 1978, and the salt formations in North America, in the United States, were mapped in the 1970s, not for gas storage, but because it was being investigated as a means of nuclear waste disposal. It was not used for nuclear waste disposal. The United States abandoned that idea and went with the idea of Yucca Mountain, which then didn't happen because of political reasons. But the salt formations were mapped. And what I wanted to show you is that the
salt formations are not as ubiquitous as in Europe, I think. I think that's true. So the opportunities for underground gas storage in the United States are porous media, depleted oil and gas reservoirs. And in fact, the vast majority of natural gas storage is in depleted gas reservoirs. And I think Shadi showed a very nice map at the beginning of your talk where you were showing where natural gas is stored in North America, and it's mostly in depleted oil and gas reservoirs. So that's, again, getting back to the question of storing hydrogen in those formations. I want to be very aware of the mineralogy and geochemistry that can happen. Okay, so here are some important processes, geochemical processes. So as we all know, this hydrogen molecule, these protons that we have given electrons to when we made it in an electrolyzer, it wants to regift those electrons and give them to something else. And so we say that hydrogen gas is an electron donor, which we've heard about from Nicole. Deep underground, the relevant electron acceptors are these: iron, ferric iron, iron 3, sulfate, and CO2. And in this talk, I'm going to focus on sulfur, because I think the reason this audience is concerned about these processes, these redox processes, is not because they all occur, because they could occur, but because there's one that's really important that could be detrimental, and that is the reaction that forms H2S. So that one's shown at the bottom. We can call it bacterial sulfate reduction. Now you notice I write this, I'm a chemist, so I write this as a reaction. I don't write the microorganisms there at all. They're merely the catalysts catalyzing this chemical reaction. And that's a little bit of a different perspective that I have from Nicole. And that's an important thing, because what I've noticed in this community and in these talks, again and again we hear the phrase microbial risk or microbiological risk. It's not the microorganisms that are the risk. It's what they can do. And I think this is the reaction that people are concerned about, the reaction that produces H2S. So I would say that it's not sufficient for H2S, for the bacteria to be there. They will be there. But that's necessary but not sufficient. There also has to be something that can accept those electrons, and that's the chemistry side of it. And that's where I think there are possibilities that minimize this risk. So let me talk a little bit about that. So Katriana, I'm going to give an example of something you said. You were talking about the microbial risk and how that is a function of temperature, and that if we go down deep enough where the temperature is above this 122 degrees C, then there won't be bacteria. This reaction can actually happen without bacteria if the temperature is high enough. At lower temperatures, it needs bacteria to catalyze it. But at greater depths, where the temperature is even higher, it can do it without the bacteria. We call those thermochemical reactions. It's just the heat will drive it. And so that's an example of, if we just focus on the microorganisms and will they live or die, we miss the point. So this is where I hope that this community can change its lingo and get away from calling it a microbiological risk, because it's natural for microorganisms to be there everywhere. I think we should call this the H2S risk or something like that. All right, so let me back to this list of electron acceptors. So the one that's relevant for producing H2S is sulfate, SO4 2-. And so for the remainder of my talk, I'm going to talk about that. The other thing I heard a lot last year and this year too is that there's a concern about sulfur-bearing rocks. And it's not the sulfur that we're concerned about. It's the sulfate. it's only the sulfate that participates in this reaction. It's not sulfide, it's sulfate. So when we're talking about the characteristics of the rock that is relevant to drive these reactions, we have to talk about the sulfate. And that was interesting to me last year when I was learning about salt caverns for the first time, because in my experience, we don't have a lot of sulfate underground, but we have a lot of it in these halite rocks. And that was interesting to me. So that's now the takeoff point for this research project that we initiated when I left this workshop last year. Let me see what my next slide is. Yeah, so let's just talk for a moment about the inorganic sulfur oxidation states. On the far right is sulfate. It has a +6 oxidation state. The typical minerals we would encounter are gypsum and anhydrite, but some of you in the oil and gas industry are very familiar with barite. For example, if you have a formation where you're trying to stimulate it by injecting seawater, you're introducing sulfate that comes from the seawater into a formation that probably has barium, and you precipitate barite and you can have formation damage. So barite is an example of a sulfate that may be a problem in some porous media. But on the left of this diagram, we have the reduced sulfur forms. So we have the disulfide ion, which has those two sulfur atoms each have an oxidation state of -1. This is a point of confusion for a lot of students who think disulfide, because there's di means -2 oxidation state, but it just means there's two sulfur atoms in the ion. The -2 oxidation state is for the sulfide ion, S2-. And pyrite is here pyrite is a disulfide, and pyrrhotite is a monosulfide. And so those types of sulfur will not react with bacteria that can do bacterial sulfate reduction. They will not. So if they are present in the rock, they will be ignored by the bacteria that would want to do this reaction. So they do not present the risk for H2S generation. So the research project that we did is this. Lauren Beckingham and I and some students. We got some halite rock samples and several rock samples from reservoirs and from cap rocks, both shale and evaporite cap rocks. And we looked at the sulfur oxidation state in those samples. Now, if you know much about chemistry and geochemistry, you know that it's pretty easy to detect elements. Like we can use fluorescence, X-ray fluorescence, to say sulfur is there or it's not. But detecting its oxidation state is trickier. And the method used for detecting oxidation state is called XANES, X-A-N-E-S. This is not something trivial to do in one's lab. I can't do it in my lab, so I had to do it at synchrotron. And it's a very special synchrotron beamline where we can do X-ray absorption spectroscopy. That includes the fluorescence part. That's the common, easier part. But it includes the ability to do this XANES analysis where you can span incident energy over very fine resolution to look at the very subtle differences in fluorescence of a reduced sulfur atom versus an oxidized sulfur atom. And so we did this for these samples that you see here. And I will acknowledge that this was done at the National Synchrotron Light Source. That's at Brookhaven National Lab in Long Island, New York. And it's a very special beamline with TES, tender X-rays, tender energy beamline. Tender meaning it's at this intermediate level, it's perfect for sulfur. Most X-ray absorption spectroscopy beamlines at synchrotrons are what we call hard X-rays, higher energy, looking at bigger elements, can't look at sulfur. So this is a very special beam line. So as soon as I got back, I wrote a proposal to get beam time at this beam line, at this synchrotron. And by January, we were there for our first time. And about 4 weeks ago, we were there for our second time. So I'm going to show you the results. And I think that this type of result is probably new to many of you. So I'm going to spend a little bit of time talking about this. On the left here is one of our salt dome samples, just a SEM image of the thin section. And on the right is the XRF, X-ray fluorescence map, which shows where there's sulfur and where there's not sulfur. Sulfur is showing up as yellow. And so you can see where the sulfur is. And what was interesting to us is that sometimes we saw it in the grain boundaries of these big halite crystals. But oftentimes we found it as inclusions, meaning it co-precipitated, not as a solid solution, but it precipitated at the same time as that salt was precipitating. So it's really embedded in the salt. Of course, if the salt dissolves, that would leave that, that sulfate. Oh, I'm jumping to the quick. That it would expose that sulfur. Now let's look at what we found out about the sulfur oxidation state. I think we already knew the answer, but we were able to use our method. Oh, I'm getting out of order here. Let me see, did I miss one? No. Okay, so I'll get to the Zanes in a minute. So I want to contrast this with this shale. The Eagleford Shale is in Texas. It's a siliciclastic mudstone with a lot of carbonate in it. On the left is the SEM image. And on the right is the X-ray fluorescence map showing where is sulfur. And we were really interested in this result because morphology tells us a lot about the mineral even before we do any analysis on it. And so we saw these sort of stringy lenses of sulfur, and we also saw round circular granular sulfur. And so, again, the question is, what is the oxidation state? Okay, so now this Zanes analysis. This is where we scan over a very small energy range at very fine resolution. It takes a lot of time to collect this data at a point. So we first had standards. And so the bottom two standards are the sulfide and disulfide standard. Pyrite is in the middle. And then you can see that they look a little bit the same, and then at the top is sulfate. And there's a difference in those peaks. So when you scan over this little short energy range at high resolution, you can see this peak separation. You can distinguish sulfate from the reduced sulfur. And so that's what we were looking for. Okay, now, so we had two salt dome samples, and we did many Zane scans of points where there was sulfur, and every time we looked, we found sulfate. We never found one example of reduced sulfur. So it seems unequivocally the sulfur that is present in the salt formations is sulfate, the one that can react with hydrogen through the mediation of bacteria to produce H2S. Okay? Now back to this Eagleford Shale that had these two morphologies of sulfur, the stringy one and the more granular circular one. And at the bottom are the two standards. And I put some arrows showing where we did these Zanes analysis, and what we found is that stringy sulfur was actually a sulfate. So this is a rock that has both sulfur types. This is a very tight shale rock. It's of interest in the state of Texas for unconventional gas production. But there they are, the two sulfur types coexisting. We looked at many, many more rocks. Mount Simon sandstone is a reservoir rock, and we there also found both types of sulfur. The limestone is an evaporite, a carbonate evaporite, and we found both types of sulfur there. But then we also looked at some rocks where we did not find any oxidized sulfur, just pyrite only. So this this is my summary chart of what we looked at. So the two yellow rows are the salt domes. We found only oxidized sulfur, the sulfate, the stuff that will react to form H2S. And the ones in orange, this Eagleford Shale, the Hammersburg limestone evaporite, and the Mount Simon sandstone, we found two types of sulfur coexisting. But then we also found some examples where there was only pyrite. That would be an example of a rock that if you put H2, if you put hydrogen gas in there, it cannot react with that sulfur, even if the bacteria are present. So this is a way I think we should start to think about this risk assessment. It's not just about, are the bacteria there? And it's not just about, is there sulfur? But is there oxidized sulfur? That's it. Now, this tool that we used, this is a research tool, a very specialized way of doing this analysis. You know, I don't have a recommendation for how this kind of analysis could be done routinely, but I think that's an interesting question to me, worth asking. And then I have one more slide, which is a photo slide of me and my colleague, Lauren Beckingham, at the synchrotron. Here in Delft, you guys ride bicycles. At the synchrotron, we ride tricycles. And there we are, riding our tricycles around the ring. It's about a mile to ride around the ring of a typical synchrotron. Thank you for your attention.
Thank you very much for a nice presentation and for nice pictures also. I'm sure there must be a couple of questions. Yes.
Oh, good.
Oh, that's nice.
Good.
It's the colleague over there, right, or not?
No, it was someone who was here yesterday.
Oh, okay. Okay, yeah.
The one where there are salt domes in Louisiana, yeah.
Thank you, Catherine, for your great talk and emphasizing the difference, the different inputs that we find actually in the soul. And my name again, Helge Lovena, Gel. And I think salt, the term salt, is somewhat misleading or being used in a misleading way very often. I think we have to emphasize this. And the reason why I'm saying this, I'm a sort of ecologist by background. So salt is used always as the term for the entire package, but that's indeed not true, right? You also mentioned that it's evaporites. And salt is only the very last part of riding over a sea, which is drying up, and that is precipitating. And there is carbonates, there is gypsum, which comes first, and the gypsum transforms into anhydride.
Yeah.
So if we have that salt package, we always have anhydride. So that's very important. It's never pure salt. We're not talking about pure salt. I've seen that so often that people talk about salt. I think it's very important to think about this and keep in mind.
Yeah. So, here's what I want to, how I want to respond to this. And you're a sedimentologist, so you know this. The other formations that are not halite rocks, that don't form these domes, for example, the silicates and the limestones, they also had sulfur when they were deposited, and it was probably sulfate when it was deposited. There's been oxygen on this earth for 2.5 billion years. So when they were deposited, there was sulfur. Why does it go away? Why does it change in those formations but doesn't change in halite is an interesting question. The process of pyritization, meaning the iron and the sulfur gets reduced to form pyrite, is something that happens over hundreds of thousands of years or millions of years. And that process, I think, happens more easily in a porous medium than in a halite rock. I just think it's interesting that oxidized sulfur gets locked in place, and it doesn't go through pyritization the way all the other formations, even those that were deposited after it. have gone through pyritization. Yeah, let me leave it at that. Yeah. Yeah. Yeah, you're right. Pyrite is not the end of the reduction line. It is pyrrhotite. So pyrite can go one more step to pyrrhotite. That's what you're talking about. Yeah, that can happen. Let me ask Nicole, is that one that a sulfate-reducing bacteria can tackle? Is yours on?
Probably,
Yeah.
yes. Yeah, so there is like pyrite reduction by microbes. I remember, I'm not 100% sure. I remember there was a PhD, during my PhD, working on this. And I think there were always indications it could be, but it's very slow and very specialized. So I don't think this is really something to be, it's not very common to say.
Yeah.
Yeah. So if it's happened, then it must be a chemical reaction.
Yeah, I also think it's
Yeah.
Yeah.
But a number of maybe add to that. But I think it happened that even at 80 degrees, and at least at 150 degrees, it was quite significant. So out of the environment.
No, indeed, as you mentioned, we are doing the high-story React project on the reactions into this pyrite pyrrhotite reduction reaction, basically, and its dependence on parameters like pressure, temperature, pH, of course, surface area exposed plays a big role, and we're using pure pyrite there to have a fully controlled experiment, right? Building also on what Trush and all found in years ago at low pressures, also at higher pressures and force temperature. Also, you see this reaction occurring during the fire pyrrhotite, which then releases indeed sulfur. And the sulfur, of course, with hydrogen dissolved in the liquid, is chemical minus So that is a reaction that occurs. What the actual risk is in the subsurface remains to be seen. Right?
Yeah.
There are many reasons why we could say that rather than pure pyrite, we have limited amount of pyrite, of course, in rocks. Usually in reservoirs, the surface area exposed, we don't really know. It's much smaller than when you stir pure pyrite with grains in the liquid, right? So. And of course, as I said, temperature, 150 degrees, I mentioned also the ice presentation is on the high side of reservoirs. Indeed, at 80 degrees, we see also conversion ongoing, but the rate is remains to be seen.
Yeah.
But then on the other hand, you have a lot of time. Operationally, I mean, it's not geologic time we should be concerned about, because, I mean, I guess we're not storing hydrogen for geological time scale, right? So, but more on tens of years. A lot of things that may reduce the risk, but still we feel like these something to keep in mind and to work on to understand.
Thanks for both of your talks. It's really very informative. Yeah, I enjoyed it a lot. So Lou from TU Darmstadt, I'm a PhD student there. And yeah, these two topics are
Whenever I talk about rates of reactions, there is a thermodynamic component, meaning there's a thermodynamic driving force, one. There's an inherent kinetic rate, like if you just have a surface, what is the rate at which atoms are exchanging? And number 3 is mass transfer. And this like Eagle Ford shale that I showed you, that is a tight, solid shale with minimal water and minimal accessibility to pore water. So that's the mass transfer kinetics are so limited. So I think that I don't have an answer for you about how fast these reactions are, but in the laboratory, we often isolate these different processes. We have ways of, we stir things to eliminate mass transfer effects. And we create far from equilibrium conditions so that the kinetics are as fast as they can be. And we do all these things to basically accelerate reactions. But I think it's still an open research question how these reactions happen underground with mass transfer limitations, et cetera.
Nicole, do you want to comment on it?
Yeah, so the methanogens, they're very, very fast, very efficient. So the biomethanation technology idea, very famous, especially in Germany, Austria. I mean, RAK has the underground sun conversion project and so on. There are several things going on. They can be really, really fast, within days. I mean, in the lab, they take sometimes just hours. So it's more the question how you actually can uphold this high reactivity over time. Yeah, that's a good question. I mean, I guess like RAK and Boku, they are really, really good at this. Hopefully they will publish also at some point what they're doing, then their results, because they claim they can actually control it very well. So it has to be seen if this is a feasible method and also in which kind of reservoirs. It will be not an option for all, that's for sure.
We also have some questions online. I will get one of them. Somebody asks, how about ferric iron? What's the abundance of ferric iron in reservoir and caprock? Sure, you can comment on that.
Yeah, for the same reason that sulfur is often reduced in sedimentary formations, iron is often reduced to. Iron exists as Fe2. It's uncommon to see ferric iron. Yeah.
Yeah, that's because of the redox conditions.
Because of the process that led to pyritization over 1 million years or more, reduced everything, not just the sulfur, but the iron also.
Yeah.
Yes, I'm Olivier from Princeton. Thank you both for your very interesting talks. Related and Tuesday and I feel there's maybe a difference that has not been that much discussed, and I would like to that we understood that that this geochemistry is the source of energy for this archaea and bacterial life. We can analyze it, but they also need the carbon sources for living. And is there a way here to select site where this carbon source for this life to happen is scarce or is rare? Like some stones with a carbonate, or is that an option that seems critical for kind of limiting the impact that can be triggered by this activity?
Yeah, that's for sure. It's a good point. So yeah, for microbes to grow, also to form biomass, they need a carbon source because carbon is a material to build their cells. They can be active without, so there's a difference between activity and growing. So if you have really minimal amounts of carbon sources, both organic and inorganic, because there are microbes which can use both, either or both, then this is a limiting factor. So it could be that you have a lot of growth and activity in the beginning. They're using up all the available carbon sources, and then it may be flattening out. Then, of course, you could still have activity because they're still there, they're not growing anymore, but they're still there. But again, for porous media, normally there's so much stuff, like there are so much often carbonates, there's always a little bit of CO2, and these guys, they can live with a little bit just. So it is for sure a factor to look out, and I always also when you talk to the operators, also with the salt caverns, please don't input any organic carbon. Look at your well fluids and work over fluids. Don't use methanol, to put into your salt cavern. It's a perfect food. So that is for sure something to keep in mind. Yeah.
Maybe I can add to that. That also you can also think of other nutrients or components of the cell which can become limiting.
Yeah.
So that, for instance, phosphate could also be a limiting factor. But as Nicole mentions, it's really hard because microorganisms can find all kinds of sources. Yeah. Okay, thank you. I will switch also to another question from the, from the digital audience. Yes. Yeah. Here somebody asks, is the effect of sulfate on rock dissolution studied?
Of sulfate on rock dissolution?
Yeah.
All right, let me start to answer. I don't quite understand the question, so let me start to say that many sulfates are quite insoluble, with gypsum and anhydrite being the most soluble, and yet many of you, like Evan, call them insolubles, right? So, so first let me just say that if you take that halite rock with those embedded grains of anhydrite, and you dissolve and you expose it to fresh water or something, then the NaCl dissolves and leaves probably the I don't know what you call it in the industry, but the stuff that collects at the bottom of the cavern, the sump. Yeah. So that's where the sulfates are, and so I start to think about this again, this mass transfer question. This is not answering this question, but I think it's a point worth making, actually. You've made the point about how insoluble hydrogen gas is. And electrons don't travel over long distances. So these bacteria have to be both at the H2 water interface to get their electrons. And then they have to transfer those electrons to the sulfate that is in mineral form. That's going to happen over an extremely small length scale. In a film, like you were talking about films. It's not just a bulk water process. So I think that these conditions, I'm thinking of lots of reasons why these reactions are going to be limited, both in extent and kinetics.
Yeah, because it relates to a question I might have to both of you, as it relates to the combination of bacterial activity and mineral behavior. How big do you estimate the risk that bacterial activity will cause mineral dissolution and thereby cause risks?
Yeah, it depends what they're doing. Like if they, for example, what kinds you have. If they are increasing, for example, the pH, then you might have some effects. If there's some other things going on, like there could be also fermenters being active, then the pH could go down. They can lead to dissolution mostly indirectly, because they need a dissolved form of sulfate. So they can't just access solid minerals, or I mean a few can, but it's again another topic. But mostly they use the dissolved sulfate. So and with these like microbe-mineral interactions, and if it's actually leading to dissolution, is not well studied. But what we know from the underground sun storage, at least they didn't have any problems with plugging. That's good. So they actually saw more like an increase in permeability. They attributed to drying effects from the gas. But yeah. So it's a potential, and then again, it depends very much on your reservoir conditions.
Mm-hmm. So this is a porous media question, permeability question, is that the point? I think that, by far, the most important chemical process that's going to increase porosity and permeability is acid. And by and large, these reactions consume protons and go swing the pH the other way, where stuff is going to precipitate and clog up pores, if anything, rather than enhance it. I think that was the question.
I don't know where the question came from in the
Okay.
online, but my question from my side, I think there's a difference between the porous system and more of a larger reservoir where integrity could be affected.
Yeah.
Yeah. Oh, yeah.
I stand corrected by using for years now the term insolubles.
Yeah.
And I'm very happy to take on board your argument. Am I allowed to call them unleachables? Because the process is leaching in the caverns, and whatever is not leached goes in the sump. And I'm very happy to put it forward, if you like, to the next SMRI conference that we have and say, guys, we're not allowed to call them insolubles. We have to call them unleachables. Is that okay?
I think you should use the word that is operational for your industry. Just don't come to the American Chemical Society and use that word in my community. But I think we understand each other.
Yeah.
When you said insolubles, I thought, well, I know what the solubility of anhydride is, and it's not zero. Nothing has a solubility of zero. Anything can dissolve. It's just really, really small. So I'm totally fine with you using the word insolubles.
Oh, I'm so pleased.
In your community, don't change a thing.
All right, I gather that.
Okay, any other questions? Yes, Bastiaan?
Yes, Bastiaan Jasma, IBN. Thank you both for a very interesting talk. I learned a lot. I have a question to Nicole. You mentioned the factors shaping a community. You didn't say much about pressure. So I was wondering, is there anything known about that? And also, since we're dealing with cyclic injection and production and the UHS, pressure will change.
Yeah.
And probably a lot. So would that... How would that influence the community?
So there's actually not so much known about pressure effects on microbes. There are actually a few isolated strains which are truly pressure loving, so they only grow under increased pressure. There are probably more, but it's, as you can imagine, they're very tough to isolate because you need to keep them under pressure at all times. And who wants to do that? So it is a thing, but we also see now from a lot of experience with the subsurface that most of the microbes, they can actually deal with a wider range of pressures. High pressure, low pressure. It doesn't seem to be like a big issue. There are a lot of possible adaptation strategies. It's mainly how the cell membrane and the cell wall is then built up. The most important thing is rapid pressure changes. And with rapid, I mean really rapid. So if you go like from 100 bar to 0 in a few seconds, you will disrupt. It's actually a very good sterilization technique. You break everything up. And it's worse going from high pressure to 0 than from like 0 to high. That will also kill a lot if you go really fast, but not so many. But from my experience, like with the salt caverns and always with the porous media, you will not have a pressure change of several dozen bars in seconds. We were talking more like 10 bars per whatever hour. So it's not a problem for salt caverns. It's not a problem for porous reservoirs. It's just really a problem for the sampling we have in the microbiology.
Okay, thank you. Well, I think in due to time, we will stop discussion here. Thanks a lot again, Nicole, and thanks a lot, Katrien.